Air, we said that an example is air. We said that is an insulator. But even in air, there will be some ions and free electrons created, for example, by the cosmic rays. And if there is a very strong electric field in that region, those free charges will be accelerated to high speeds. They will collide with other molecules in the air or whatever insulator you have. And they can be also ionized. So you get this avalanche of ions in your system. So although since it's an insulator, they have a very few ions, mobile ions. If you exert a sufficiently high electric field, you will get many ions that will be ions or electrons that will be free to move in your system. This is what we call an electric breakdown, because once this happens, your insulator becomes a conductor because of these mobile electrons in your system. Now for air, this breakdown electric field is typically around 3 times 10 to the power 6 volts per meter. But this also limits how much voltage you can apply to, let's say, a sphere. Now, in this example, first we will show that the voltage, the voltage for a sphere, the breakdown voltage for a sphere is proportional to its radius. And then we will calculate it for a sphere of radius of 5 millimeters. So we had already seen that if we have a conducting sphere, the electric field has a magnitude 1 over 4 pi epsilon 0 q over r squared. This is outside the sphere. Right on the surface of this sphere of radius r0, if we call the radius r0, then the magnitude of the electric field on the surface would have this expression. Whereas the voltage on the surface of this conductor will be 1 over 4 pi epsilon 0 q over r0, which is nothing but r0 times E. So V is equal to r0 times E. Now the maximum electric field we can create using such a sphere would be just this much if the sphere is in air, because if we create a larger electric field on the sphere by putting more and more charges over there, the electric field becomes larger than this breakdown voltage, breakdown electric field, and hence the air becomes a conductor and it will leak away. So it won't stay on the sphere. So we see that the maximum voltage you can apply in this case is actually proportional to the radius of the sphere. The larger the radius of the sphere, the more charge you can put inside on your sphere. And for a sphere of radius 5 millimeters, this breakdown voltage will be 5 times 10 to the power minus 3 meters multiplied by the breakdown electric field for air is 3 times 10 to the power minus 6 volts per meter, or plus 6 volts per meter. And this is just 15,000 volts. So if you have a 5 millimeter small sphere, and if you apply a voltage that is larger than 15,000 volts, you will create an electrical breakdown. Now, for example, this also tells us that if we have very sharp tips. Now, this point, you can just consider it as a very small sphere. So for a very small sphere, if, for example, there is a thundercloud, it will create a large potential difference between the tip and the thundercloud. And the potential will be large, but if it's a sharp tip, R0 will be small, so you create a large electric field on the tip. And since there is a large electric field on the tip, there will be the charges will leak away, so there will be a flow of charges. And if this flow is, let's say, slow enough, then the charges will just they will move to the cloud and they will neutralize the charges on the cloud. So this is basically the working principle of a lightning rod. In certain cases, when you have such large electric fields at sharp tips, as the charges are moving, they can excite the molecules nearby. And when they excite the molecules nearby, you can see some light coming out. So that is what we call the corona discharge.